right, any questions? All right, on to sorts. So we know bubble sort, right? So bubble sort, you make a pass through your data from top to bottom, and at each point you check to see if a pair of numbers are in the wrong order relative to each other. If we're going largest at the bottom, the 10 and the 4 have to swap, the 10 and the 2 have to swap, the 10 and the 6 have to swap, the 10 and the 5 have to swap, and so on. And the effect is that 10 is sort of falling down to the bottom of the list. Okay, so the light numbers are bubbling up, the heavy numbers are sinking down. This is one pass. Once you finish that, in the remainder of the list is the second largest number, and that will have the effect of sinking down to the second to the last position on your second pass. There's other changes being made as well, right? The 2 and 4 will swap. The 6 will stay there and swap with the 5. The 7 will stay there, the 8 will swap with the 1. And now you have two numbers in the correct spot. And so after n passes, you have n numbers in the correct spot, and so your list is sorted. So we talked a bit about order of complexity on Monday. This is an order n squared. And you can improve the time it takes a few ways. One way is to, on each of your subsequent passes, only analyze an earlier piece of the list. Don't go down and try to resort your largest numbers that have already been placed in the correct spot. That brings you to a roughly order n squared over 2. Another option is, as you go through each pass, you can set a flag anytime that you swap numbers. And if you get to the end of the pass and you haven't set the flag, you're done. So if your list was sorted to begin with, one pass you should be able to notice that your list is sorted and be done at that point. So there you've got a best case of order n, right, one time through the data. But average case is still going to be n squared, regardless of these embellishments. There's a lot of data movement taking place, but it's mostly close proximity, right? Swapping two numbers in memory is nearby memory operations, but, you know, if the 10 started off up here, it's going to get moved down to the end of the array, but it's going to hit all the spots in between on the way there. And memory access is one of the factors that can play a big role in how efficient an algorithm is, which we'll see with some of these other versions of sorts. So that's bubble sort, right? Pair of nested loops n times through each pass. Each pass is in operation, so order n squared. So selection sort. And you want to understand these sorts. You want to be able to, on a test, either take a piece of data, a set of data, and perform a sort on it, or look at the operations performed on a set of data and identify what the sort was, or answer questions about order of complexity, or possibly code up pieces of some of these algorithms. So things to think about as we go through these. So selection sort. So here's our original set of data. And let's say we want to sort from smallest to largest. So each pass, pick, let's say, the smallest number and append to the output. So here's our output array. So here's what a selection sort does. We run through here and we try to find the smallest number. Well, how do we do that? I've got 2 2's in here. Let's make that a 1. How do we find the smallest number in a set of data? Well, we just start off with the first number and we say that's the smallest. We look at the second. Is that smaller than the smallest we've seen? Yes. So our smallest is 4. Is 1 smaller than 4? Yes. So that's our smallest. Is 3 smaller than 1? No. And by the time you get to the end, you found the smallest. Okay, so a running minimum, kind of what you do in PA5. So make a pass through your data and decide what the smallest piece of data is. And you need to know what the value is and also where it is in the array. So in this case, one pass through will identify that 1 is the smallest element here. Put that in your output array. And somehow remove it from your input list. Okay, set a flag, clear a flag, something. Okay, so one pass, we've got the smallest item in our output. Make a second pass. The smallest value in the remaining set of numbers is a 2. Add that to the next spot in your output array, remove it from your input. Go through, the next item is 3. Remove that from your input, add it to your output, and keep going. There's a 4. Smallest item is 5. Go through, smallest item is 6. Run through again, smallest item is 7. Go through the remainder, smallest item is 8. Next pass, smallest item is 10, and final pass, smallest item is 15. So it's called a selection sort because the sorting is happening in how you select numbers from the input. Okay, this is my mnemonic for remembering this versus the next sort, which is an insertion sort. The selection happens when you select which things to add to your output. And so each pass is order n because you have to look through n pieces of data to find the smallest, and you have to do n passes. So this whole thing is order n squared. Depending on how you do it, you can reduce each pass to be, order n, n minus 1, n minus 2, and so on, and you end up with the n squared over n order of a refined bubble sort, but it's still order n squared. So how do you pick the smallest from the list, right? You just go through, you keep track of the running smallest and its location in the list. How do you remove it from the list so that you don't look at it again?
Set to some value or
You could set it to infinity, right? If you're looking for the smallest and you have a notion of infinity, you could set it to infinity and you won't pick it again. That's one option. Other options? So you could shift everything, which is expensive. That'll make it an order 2n times n squared. We don't really care about the order of this, so instead of shifting, here's what you could do. After you pick the 1 and you've put it in your output list, you can take the last number and move it up there and just say my list is now only n minus 1 elements. Now I don't need an infinity, I don't need to somehow skip it, right? I'm always sort of keeping these, and that's a cheap operation. It's a fixed number of steps. If you have a structure with a flag, right, you can have some flag, and when you pull off a piece of data, you can set that flag. And then only pay attention to things where the flag is clear. All of these things have potential costs, right? The flag approach works great, but if you have to initialize the flags, you're adding more time. But if it's just a setup cost, that may be worth it. If you had these things in a linked list, you can just delete from the list. So there's different options there. But nominal performance is going to be n squared. Okay, so that's selection. We're selecting in the correct order. Our other n squared sort is an insertion sort. An insertion sort, the sorting happens when you insert things into your output list. as opposed to selecting from your input list. So we take from the input in order. We just start with the first number and we just march through this from beginning to end. So there's no hard work done in choosing your numbers from the input. The hard work happens when we place them into the output. So we take the first number 10. There's nothing in the output yet, so that's just going to go in the first location. And we're done with that number. Now we move on to the second number, which is a 4. And we say, where should that go in the output list? Well, it should come before the 10. So we put the 4 right there, and the 10 moves down. And now we're done with the 4. Now we look at the 3, and that should go before the 4, so somehow we put that in before the 4. The 4 moves down, the 10 moves down, so that's our list. And we're done with the 2. Take the next number 3, that comes after 2, it comes before 4, so we put the 3 right there. The 4 goes there, the 10 goes there, and we're done. And you keep going, and when you're finished, your output list will be the sorted list of numbers. So it takes n passes, right? Each pass we're taking one new number from the input and putting it into the output list. It takes n passes. What's the complexity of that inner pass, of inserting something into the output list? If you have to shift everything around, it's order n. Can we avoid shifting? We could use a list. Like that. I'm not cheap beer sick, by the way. But I've had a dry throat. So talking makes it drier. If we have a list and we want to insert a 3, just do that. What's the order or complexity of that,
Still going to be order n.
It's still order n. Why?
Reverse.
Yeah, because you have to find where to insert. So marching down the list potentially takes you n steps. Once you get to the right spot, it's a fixed amount of time to insert. So a list will still be order n. If we used a binary tree, we can get to log n. And we're not really doing an insertion sort anymore. So this is nominally going to be order n squared also.
If you used a binary tree, does that also have a different name?
That's really just kind of building a binary tree.
I think you just named it Quicksort. That would be n log n, wouldn't it?
That would be n log n. I don't actually know if there's a name for sorting where you're putting things in a binary tree and then traversing, because it's kind of like the thing you do. Yeah, I don't have a fancy name for that. All right, so you got the difference between selection and insertion. Selection, you do the work in choosing from your input, selecting from your input. Insertion, the sorting happens when you insert into the output. Okay. And this, I've mentioned before, this seems to be how I sort papers. Right, because I get a stack of papers turned in, and I take the first paper, and that's at the top of my pile, and I take the second paper, and it goes before or after the first. And I take the third paper, and it goes before the first, in between, or after the second. And I keep putting them into the right spot, so I'm building up the sorted list in my hand. I'm just taking the papers from the top of the input list. So that seems to be one way of doing papers. Okay, so those are order n squared sorts. And that's great for quick and dirty, but it's not good for, you know, a billion pieces of data, which is not unusual, right? If you're doing financial processing, right, you're easily dealing with, you know, a billion pieces of data. So sorting becomes an issue. So let's talk about some n log n sorts. So a merge sort. The merge sort's also what I do when my stack of pile gets too big to do a straight insertion sort. So merge sort is really simple to describe. It's a bit of a pain to code and see. So there's a list of numbers we want to sort. Well, suppose we split our list in half and we somehow sort the first half using, you know, whatever method we like. Here's a 2, 3, 4, 6, 10. And the second half, here's a 1, 5, 7, 8, 9. So I have two sorted sublists. It turns out that taking these two 5-element arrays and turning it into a sorted 10-element array is really easy to do. We can do it with a single pass through the data. And here's how we do it. We look at the first element in each array, whichever one is smaller, that's the first thing we put in our output. And then we mark that off when we go to the next element. So now we're looking at a 2 and a 5. 2 is the smallest, we put 2 in our output. Now we're looking at a 3 and a 5, that puts a 3 in. Now we look at a 4 and a 5, that puts a 4. Now we're looking at a 6 and a 5, 5 is smallest. Now we're looking at a 6 and a 7, take the 6. Now we're looking at a 10 and a 7, a 10 and an 8, a 10 and a 9, and then finally our 10. So merge sort, you have two piles that are sorted. And at each point you just look at what's on the top of each pile and you take the smallest of those two and add that to your output. And whichever pile you took the smallest from, now there's a new number on top of that. Look at the smallest of the two piles, take that, put it into your output, and you just keep going. So if I have 60 papers, I can do insertion sort for probably 30 of those, but after that it gets to be such a big pile. If you've got 55 papers here, and you take the next one off, you have to search through 55 papers to figure out where to insert. That gets to be a lot of work. So sometimes I'll do insertion sort and get two piles of about 30 papers each, and then just start pulling off the top, right, to put them together. This is also what I do with exams, where I've got two sections. After each section has turned in their exams, I've usually sorted those up. I have to combine them into one big pile. Just grab the smallest from each pile and keep putting them together. So here's what a merge sort looks like. This is going to be really pseudo code. So let's merge sort an array of data containing n pieces of information. So this is meaningless notation, it's just pseudocode. But take an array containing, say, the first n over 2 pieces of data and sort that. And then sort an array containing the other elements of that array. And I'm ignoring, you know, if the number of elements is odd, all of those details. But basically chunk your array in half, somehow sort the first half, then sort the second half, and then merge data 1 through n over 2 with data n over 2 plus 1 comma n.
Would it be any more efficient to do to like like split it up several times?
You can do that.
Does that change anything?
Yeah, if you were to split it into, say, 4 pieces, you have more work to do when you merge, but the things you have to sort are smaller, so that step is quicker. I don't know where the sweet spot is. I'm going to guess if you split it 2.7 times, you get your optimal.
Yeah.
But yeah, that'll definitely affect it. So yeah, somebody used the R word. So how do we do this sort? How do we sort the subarrays? What's our best choice here?
Bubbles.
Bubble sort, I like it.
We're just keep splitting them until it's trivial.
Yeah, let's do a merge sort. If merge sort is really such a good sort, let's go ahead and use it to sort the subarrays. So call merge sort on the half lists, take the results, merge them together. Where does the recursion end? If n equals 1, or maybe if n is less than or equal to 1, then there's nothing to sort, and so just return. Otherwise, split your list in half, merge sort each half, merge them together. So this part, there's nothing to write. Right, this is an if statement, these are 2 calls. The only thing you have to write for a merge sort is this process of merging, of interleaving these 2 subarrays into a larger array. And merging is pretty easy. Simply go through n times, or n pieces of data. A and B are our 2 subarrays. Next A and next B are initialized to 0. So if A bracket next A is less than B bracket next B, add A bracket next A to the output and increment next A. Otherwise, add B bracket next B to the output and increment next B. The only slightly tricky thing you have to make sure about in here is that these things make sense. Because it's possible that next A will get to the length of the elements in A, and trying to look at A bracket next A will seg fault. Right, so this happens if you're trying to merge a pair of lists like right, if you try to merge these, well, your output's going to get 1, 2, 3, 4, 5. You're going to consume these things. Next A is going to be pointing past the end of your data. Next B is still pointing at your first thing. Well, you need to recognize that next A is a value saying you've used up all your elements from A, and so from that point on, just copy everything from B into your output. Details. But that's the essence of it, right? Just compare the beginning of each of the remaining things in your 2 lists, pick the smallest, add it to your output. Right, so output bracket I equals, and do that through. So merge sort is not a lot of work to write. Okay, it's a merge operation. There's edge cases, but other than that, it's a pretty straightforward algorithm, and all the work's being done recursively. So this merge step is order n. Right, if you have n pieces of data, you basically have to do some kind of loop. that runs n times, and the amount of work in here is independent of the size of the data. But these recursive calls, each time you call merge, you're going to get twice as many calls to merge. So depending on how many times you split this thing in half, you're going to get 2 to the n that many times that you end up calling merge sort. Which is 2 to the n that many times that you're going to end up calling merge. But merge is not always order n. In fact, it's only order n the first time that you call merge sort. This call to merge sort will be working with 2 lists that are size n over 2. In that case, the merge is going to be order n over 2. Now, asymptotically, we can ignore constants like 1/2. But when we actually look at the analysis, most of the times that we do this merge step, it's less than order n. In fact, most of the time it's less than order n over 2. And so if you actually do more than an approximate calculation, this whole thing should end up around n log n.
Is there a name for that series? That n, n over 2, n over 4, n over 8, n over
It's a geometric series.
2?
Yeah. So n log n is a good place to be sort-wise. And so a term you'll see for this kind of algorithm is divide and conquer. Right, because we take the original problem, we split it into smaller subproblems, we solve those, and then we put the solutions together. And divide and conquer more often than not involve recursion. All right, questions on this? All right, so our next sort is Quicksort, and this one is more funky. And this one will actually work out on the board in groups after we talk about it, probably tomorrow. It's another divide and conquer sort. It's going to be order n log n average case. Interestingly, Quicksort is order n squared worst case. And the worst case is if your data is sorted to begin with. And so some algorithms will actually just scramble your data before it goes through Quicksort, just in case it happened to be sorted or close to sorted to begin with. You'll get better performance by mixing it up first.
Couldn't you also just check to see if it's already sorted?
Yeah, but if it's close to sorted, it still gets really bad performance. Like if you've got a sorted list and you just inserted one thing at the end of it, Quicksort will be pretty abysmal.
Huh.
So yeah, throw it on the floor and mix it up first, and you end up with a win.
It's also bad with duplicates, unless you use two-way partitioning, right?
I don't know about that. I could see that though.
I think Dijkstra is like a three-way partition version.
Oh yeah, yeah. So the general idea of a quicksort is to take a number and move it into its rightful place in the output. And so we start with a number called the pivot. And often the pivot is just the last number in the array. And we're going to make a pass through our data, and the goal of the pass is to put the 5 into the correct place it should be in the final sorted array. We're not worried about anything else about the list, just making sure 5 goes in the right spot. So So we have a pair of pointers, one from the left and one from the right. And we start off from the left, and we ask the following question: is this number less than the 5? Okay, 10 is not less than 5. So we stop moving at this point. And let me change my numbers here. Make them a little more interesting. Okay, so we stop here at the 10, and we start off on the right, and now, moving in from the right, we ask, is this number bigger than a 5? And it is. So we move over and we say, is this number bigger than a 5? And it is. So we move over and we say, is this number bigger than a 5? And it's not. Okay, so what do we have at this point? We have a number over here on the left which is too big, and a number over here on the right which is too small. Okay, we're going to swap those. So this is going to become a 4, 7, 2, 3, 10, 6, 8, and 5 is still our pivot. And the arrows show which numbers we've considered so far. Okay, after we swap, we go back to the left, we start from the next location we haven't seen yet, and we continue this process. Look at the 7, is that smaller than a 5? No, it's not, so we stop. And we go over to the right, and we look at a 3. Is that bigger than 5? No, it's not. So these two are in the wrong place relative to each other, right? Our goal is to have the smallest number over here on the left, and the largest number over on the right. So just compared to 5, this number is bigger than 5, this number is smaller than 5. That tells us this number is bigger than that number. And we want the smallest numbers to be on the left, so we're going to swap those two. So now we get a 4, 3, 2, 7, 10, 6, 8, 5. We've tested all of these numbers. And now we go back, we start from the left. Look at the number 2, is that smaller than a 5? Yes, it is. And we were at a 7, so when we move over, we collide with the 2. Okay, our pass is now finished. And this last number that we were looking at, we're going to swap that with the 5. And now our list is going to look like 4, 3, 2, 5, 10, 6, 8, 7. Okay, what we've done is we've moved every number smaller than 5 to be to the left of 5. And every number bigger than 5 is to the right. Okay, in moving over from the left, any number that was bigger than 5 got swapped with something that was smaller than 5. So when our arrows collide, everything to the left must be smaller than 5. Everything from that arrow to the right is bigger than 5. Well, if everything to the left is smaller than 5 and everything to the right is bigger, that 5 must be in the correct spot. Right? If that 5 belonged over here, would mean there's some other number smaller than 5 that should be sitting here. So this 5 is in the correct spot. Well, we did all that work. We got one number where it should be. But this is order n to do one of these passes. Right, we basically just moved in, we examined n pieces of data and did some swapping along the way. So it's order n. Well, since everything over here is less than 5 and everything on this side is bigger than 5, if we somehow now manage to sort this array and manage to sort that array, our entire array will be sorted. Because this will be a sorted list of things less than 5. There's our 5. This will be a sorted list of things bigger than 5, and we're done. So how do we sort this subarray? Use a quicksort. So quicksort is 3 steps. 1, make a pass that takes the pivot and moves it in the correct spot. 2, do a quicksort on everything to the left of the pivot. 3, do a quicksort on everything to the right of the pivot. And so it's another divide and conquer recursive algorithm. So let's sort some letters. So here's our pivot is G. Smaller, smaller, bigger, 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 smaller. Swap these. This will become an F, and this will become a T. Move over here, smaller, move over here. We've hit the arrow coming from the right. So swap the G into here, swap the T with the pivot. This is now in the correct location. Now do a quick sort on these. So there's your pivot, smaller, 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 smaller. And we've hit the end, so the T is in the correct location. So now we have to do a quick sort on this and a quick sort on this empty list to the right. There's our pivot, smaller, smaller, smaller. We've hit the right arrow, so the O is in the correct location. Do a quick sort on the list on the left, do a quick sort on the empty list on the right. Right, this is where we're breaking down to an order n squared instead of n log n, because each time that we divide our list, we're really not splitting it in half. We're taking one thing off the end. So H-J-I, there's our pivot I, that's smaller, that's bigger, so we swap the I and the J. This is in the correct location. Now we have to quick sort 2 singular lists, and that's our base case. So Hij is already sorted. That's the return from here, so this returns Hijo. That's the return from sorting this, so this is Hijot. That's the return from sorting this. And the G is in the correct spot, and we do the same thing on that list on the left.
So you're starting from the left and moving to the right until you find something that's bigger.
Yeah, so you get a pair of pointers. Start from the left, we're looking for things smaller than the pivot. Move over until we find something bigger, stop. Then move from the right, look for something smaller, stop, swap those.
So like,
And then continue.
with the previous example, if you're sorting the 4, 3, 2 one, you start out with something that is bigger, and then you start out with something that is bigger on the right as well, and then you have that collision.
So wait, like 4, 3, 2?
Yeah,
Is there a pivot?
2 would be the pivot,
To the pivot, okay.
right?
So we start off with that, that's too big. We start off with this, that's too small.
That's too big.
That's, yeah, that's bigger, that's fine. So we move over and our arrows collide.
Right. And so then you would swap the 2 and the 3?
Yes.
Okay.
No, you swap the 2 and the 4.
But I thought that before when we did that swap, we swapped the 5 and the 7.
Oh, let's see if I can find it.
So I was taking the pivot and replacing it where we had that.
So this one,
Yeah.
I I misdrew my arrows, I believe. So we had arrows here and here and here and here and here. Okay, and we had just swapped the 3 and the 7. Okay, so now we continue from the left. We look at the 2. That's smaller than the 5. Okay, so we move over, and at that point we collide with the arrows from the right.
Oh, so you're moving the 2 over because you're looking, gotcha.
Yeah, so then we swap with the one where the arrows collided.
Okay, I was thinking it was the other arrow there.
I should be using 2 colored arrows or something,
Yeah.
but my colors aren't convincing up there.
Okay.
Yeah, so start from the left, keep going as long as your number is smaller than your pivot. If it's bigger than the pivot, stop. If you collide with the arrow from the right, stop, right? And at that point, swap with where you are, where the 2 arrows collided. It is quick, though. Like if they called it the slow sort, nobody would use it, while some people would.
People use double sort.
Yeah, yeah. And I always want to spell it without the C, but I think it's got a C in it. So order of complexity, right? So each pass is order n, right? Moving through and finding the spot where you want to swap with the pivot, but with your n getting smaller each time, and nominally each pass cuts your list in hopefully in half, right? If your pivot ends up around the middle, you end up with 2 lists that are half the size, and your recursion kicks out when you get down to a list with a size of 1. That's a base case, so it's roughly log of n passes. And so this turns out to be n log n. But that pathological case, where this is your pivot, it's already in the correct spot, you're not going to move it, you're going to end up calling quick pass on this, and you'll find the 7's in the correct spot, and so you won't move it, and you'll end up calling quick pass on this, and so in this case you end up doing approximately n passes, and so that's actually order n squared, worst case. So it's a bubble sort. It's a recursive bubble sort. And so coding this takes a little more work. You gotta deal with edge cases, right, like this. Probably the hardest thing in C is with some of these divide and conquer sorts is dealing with the arrays, right? If you have an array, of 100 numbers, and you want to split it in half, right? Well, you know, that's the way I can address a subarray starting from element 0, right? And I need to somehow know how many things are in an array, because that's not part of an array, so, you know, presumably you're passing the address where the array begins and then the number of elements in the array. So this is the first half. If I want the second half, you can actually do something like this. And you say ampersand data bracket 50. That passes the address of the 50th element. Well, that's to a function that's just getting an integer pointer. That looks like it's getting an array that happens to start at element 50 in that original array. It doesn't know that it's part of a bigger array with 100 elements. It just sees a location in memory. And if my sort function is getting an integer star x, right? X bracket 0 will be data bracket 50. X bracket 5 will be data bracket 55. So you can play games like that with the indexing, but you got to worry about edge cases. And if you're trying to pass back a sorted array, that can get ugly. So there's mechanics that in C in particular don't play very nicely. But the actual algorithm itself, pretty straightforward. All right, so we'll spend some time tomorrow doing quick sorts on the board to make sure you understand that, and then we'll talk about merge heap sort as another n log n sorting algorithm and another data structure on its own. And Friday I'm going to do as an open lab again. So Friday won't be any new material. We'll have time you can come in and work on your programming assignments and such, and I'll be here to interact with you.